everyone, let's go through the experiment on fluid friction measurement in piping system caused by pipes and also fittings. There are four objectives for this experiment. First is to understand the effect of the roughness of internal surface area over a piping system. Then relate the pressure drop and the friction loss in piping system. This continue with the understanding the effect of different flow rates on the friction loss, and the last objective is to understand and calculate friction loss over different types of fittings. A common differential pressure gauge is used in this experiment to measure the pressure drop in piping system. This pressure drop is usually due to the presence of various types of pipe fittings and also valve components. The pressure drop is an effect of friction loss in the piping system. The friction loss through piping system can be divided into two, such as major loss and minor friction loss. Major friction loss is due to the roughness of pipe wall and viscous effect, which is laminar or turbulent flow of the fluid, while minor loss is caused by the fittings in the system. If an ideal component without any friction effect, it is behave like a straight pipe section of length equal to the component flow path. The frictional effects can cause additional pressure drop in piping system. Roughness of pipe wall is the major cause of frictional loss in piping system, and it affects the pressure drop of flowing fluid. The effect of pipe roughness can be described by the flow area constriction, and roughness of pipe wall increases the shear stress. The relative roughness of pipe, which related to the friction loss in piping system, is used to determine the friction factor. Relative roughness of a pipe is the ratio of roughness of pipe to the internal diameter of pipe. Apart from roughness of pipe wall, flow rate also affects the friction loss in piping system. The effect of flow rate on friction loss depends on the viscous effect of the fluid, either laminar or turbulent flow. In laminar flow, friction losses are proportional to fluid velocity, that the velocity varies smoothly between the bulk of fluid and pipe surface. The fluid velocity at surface of pipe is zero. This is due to the presence of shear stress. The roughness of pipe surface influences neither fluid flow nor friction loss in laminar flow. In turbulent flow, friction losses are proportional to the square of fluid velocity, and here a layer of chaotic eddies and vortices near the pipe surface called the viscous sublayer forms the transition to the bulk flow. In this case, the effect of roughness of pipe surface is considered in terms of relative roughness. For transition flow, where the Reynolds number in between 2000 to 4000, the fluid flow is unstable and varying with time as vortices within the flow form and vanish randomly. And then the friction loss in this transition type of fluid flow is not well modeled and well understood. Friction factor based on relative roughness and Reynolds number can be obtained from Fanning's friction factor chart or Moody's friction factor chart. So from this we can see that the total pressure drop in a horizontal piping system is the total friction losses due to the pipe length that measured along the center line of pipe plus the sum of additional friction losses due to various fittings, valves, expansion or contraction. Again, to determine the friction loss in piping system. Differential pressure gauge DPG is used to measure the pressure drop between two points along the pipe that simultaneously connected to DPG. If we want to calculate the friction loss for one component, then two differential pressures must be recorded. One is differential pressure due to components plus its associated length of upstream or downstream pipe plus flow path length of component itself. Another differential pressure is due to similar types and size of pipe with a straight run of length. We must make sure that the two recorded differential pressures are taken at the same flow rate. So that's all for theory part.
For description of equipment, basically, this apparatus consists of three pipelines, which is galvanized iron 1, GI1, stainless steel 1, SS1, and galvanized iron 2, GI2. The difference between galvanized iron 1 and galvanized iron 2 is galvanized iron 1 is used to circulate water from tank 1 to tank 2, and galvanized iron 2 is used to flow water from tank 2 to tank 1. For galvanized iron 1, its nominal diameter is 1 inch and also known as pump discharge pipeline of galvanized iron 1. This pipeline is used to circulate water from tank 1 to tank 2 with the help of pump. This is because the location of tank 1 is lower than tank 2. The length of pipeline GI1 is 1144.27 cm. This length is measured from pressure gauge 2 to the discharge end. As we can see, there are a lot of pressure gauge and common differential pressure gauge DPG along this pipeline. The main function of the device is used to measure the value of pressure and pressure drop. For stainless steel 1, its nominal diameter also 1 inch and also known as pump discharge pipeline stainless steel 1. The function of this pipeline is similar with galvanized iron 1, which is to circulate water from tank 1 to tank 2 by using pump. Its approximate length is 1187.45 cm. If we look in the lab, pipeline stainless steel 1 is located beside pipeline galvanized iron 1 because one of the objectives of this experiment is to investigate the effect of the roughness of the internal surface area over a piping system. If compared to galvanized iron 1, stainless steel 1 has smoother surface of flow and longer length. Different with galvanized iron 1, galvanized iron 2 has two nominal diameter, which is 2 inch and 1.5 inch. This pipeline is known as gravity discharge pipeline of galvanized iron 2 because its function is to return water from tank 2 to tank 1 by using gravity. The reason why it has two nominal diameter because this pipeline consists one reducer inside it. So, if the flow rate flows from tank 2 is 320.04 cm3 for 2 inch diameter, then the flow rate for 1.5 inch diameter will increase to 3 to 1.31 cm3.
Now we will move to principle of operation for this experiment. Before we begin with the experiment, we need to follow of this principle. First and foremost, we must ensure that tank T1 is full of water until it reaches its maximum level. Then we need to check all the pump bypass are fully open and the differential pressure gauge switch are at 0 of position. Switch on the power supply and start pump GI1 and practice operating the pipe by opening and closing the appropriate discharge valve. Bear in mind that we can operate GI1 and SS1 simultaneously. Then we need to try to operate with the level of tank T2 is constant, with the drain valve and the overflow is shut, and just by adjusting the inflow from GI1 or SS1 only. Next, we need to use flexible measuring tape and ruler to measure the corresponding pipelines and try to compare the measurements with the values provided. Lastly, we need to read and understand the procedure for the differential pressure gauge measurement. Now I will explain an example on how we taking the DP readings. So for run 1 by using GI1, we need to make sure that panel selector switches for GI1 and SS1 be at the first 0 of position. Then we need to isolate pipeline SS1 by shutting its discharge valve located upstream of PG3. Next, we need to set the flow rate for pipeline GI1 at 24 USG/PM by regulating the pump bypass valve. And make sure that selector switch for SS1 remain at the first 0 of position throughout this run. Now I will show operator selector switch for GI1 clockwise 1 for the first of DP readings. First, we need to start at the first of position and select 0 clockwise of position 1. Then equalize for a few seconds and read the DP as equalizer. Next, switch to position 1 and read the change in DP from previous 0 position as DP lamina. Then select clockwise net 0 and equalize for a few seconds and read the DP as equalizer. Select position 2 and read change in DP from previous 0 as DP elbow plus lamina. Then select clockwise net 0 with equalizing for a few seconds and read the DP as equalizer. Select position 3 and read change in DP from previous 0 reading as DPT plus valve plus lamina. Then select clockwise net 0 and equalize for a few seconds and take the read as DP equalizer. Select position 4 and read change in DP from previous 0 position as DP expander or reducer plus lamina. Then select clockwise net 0, which means is the last 0 and the end of the reading for clockwise 1. Before we take the reading for position 1, 2, 3 and 4, we must make sure that there is no bubble inside the tubing by pressing the DPG button. Next, for the operator selector switch for GI1 anti-clockwise 1 for second set of DP readings. First, we will start at the last clockwise 0 position and read the DP as equalizer. Then we select position 4 and read change in DP from previous 0 position as DP expander or reducer plus lamina. Next, select anti-clockwise net 0 and equalize for a few seconds and read the DP as equalizer. Repeat the operator selector switch for GI1 clockwise, but we read it anti-clockwise for position 3, 0, 2, 0, 1, 0, and that is the end of anti-clockwise 1. Next, for operator selector switch for GI1 clockwise 2 for third set of DP readings. First, we select 0 clockwise from position 1, then we equalize for a few seconds and read the DP as equalizer. Then we select position 1 and read the change in DP from previous 0 position as DP lamina. Then select clockwise net 0 and equalize for a few seconds and read the DP as equalizer. Repeat as per clockwise 1 for position 2, 0, 3, 0, 4, 0, and that is the end of clockwise 2. Now I will present for the experimental procedure for this experiment. So for the first procedure, we operate pipeline for GI1. Firstly, make sure the discharge valve in SS1 is shut. Then start the pump to operate the pipelines GI1 and GI2. The bottom drain valve of T2 should be remain shut, but all the side overflow valves are open. Then the valve along GI2 should be fully open for water to gravity flow from T2 back into T1. Next, we need to adjust the flow rate in GI1 to 15 US-GPM and take the various pressure and DP readings. Make sure all these readings are taken at the same flow rate. Refer to the previous section on taking DP readings for further instruction. First set of readings should be taken, which is clockwise 1, anti-clockwise 1, clockwise 2 and anti-clockwise 2. Next, we need to record all the data we get from the experiment in table 1A. And then we need to compute the average DP value and then transfer this file to table 1C. The following are the pertinent data: F1, which is rotameter, PG1, PG2 and PG4. These are the formula to calculate DPG for laminar flow, DPG 90 degree elbow only, DPG T plus gate valve only and DPG expander or reducer only. Then we need to repeat for run 2 at flow rate of 11 US-GPM and record the data as run 2 in table 1A and 1C similarly.
At flow rate 15 US-GPM with discharge valve in galvanized iron 1 shut, operation in pipeline stainless steel 1 is similar with operation of pipeline galvanized iron 1. For run 1, after repeating procedure 1, take the pressure value and TP reading at 15 US-GPM. Then repeat the procedure for run 2 at 11 US-GPM. Record all the data in table 1B and calculate average DP values and transfer the data to table 1C. For procedure to operate galvanized iron 2 with galvanized iron 1 or stainless steel 1, first of all, shut all the overflow valve at tank 2. The only outflow from tank 2 should be through galvanized iron 2. The 2-inch gate and 1.5 globe valve at galvanized iron 2 should be fully open. For run 1, operate galvanized iron 1 at 15 US-GPM as inflow into tank 2 and record rotameter flow rate reading F1 as the flow rate through galvanized iron 2 in table 2. Then measure the hydrostatic head value and record in table 2. Hydrostatic head is vertical distance between constant water level of tank 2 and the terminal discharge end of galvanized iron 2. For run 2, repeat the previous step by using 10 US-GPM as inflow. Last but not least, repeat procedure at run 1 and run 2 by using stainless steel 1 and record the data in table 2.
Right now, let me continue with the results and discussion of this experiment. As you can see from table 1A and table 1B, the differential pressure gauge denoted as DPG and pressure gauge denoted as PG are collected from the procedure that has been conducted just now, which are galvanized iron 1 and stainless steel 1 respectively. The flow rate suggested in the lab manual is 24 US gallons per minute. Somehow, problems arise when we use this. This is because the pressure drop reading cannot be read as its range is too small. To the point we can assess the reading, the values of flow rate chosen for this experiment are reduced to a little bit smaller, which are 15 US gallons per minute and 11 US gallons per minute. We move on with Table 1C. This is the overview of the results collected and calculated. Basically, data from Table 1A and Table 1B are transferred to this table known as Table 1C. Let's look at this closely. The values of pressure gauge and differential pressure gauge are taken from Table 1A, which correspond to 15 US gallons per minute flow rate for galvanized iron 1. As the formula are already given, we can just easily calculate it for differential pressure gauge. Let's take a look at this sample calculation for 90-degree elbow. The last row is needed for us to find the velocity, velocity head, and also Reynolds number. This is the sample calculation of finding velocity, where the flow rate is divided by area. The formula of velocity head already given, and the formula of Reynolds number is rho UV over mu. The higher the flow rate, the higher the Reynolds number. We can continue the same steps with the rest of 3 columns that have different flow rates and different types of pipes. For Table 2, the chosen pipeline is galvanized iron 1. This is because if the stainless steel one is used, the reading might not be read, as for the first experiment, the value of reading was already small. It might not show so much difference in values as the reading range is so limited. To avoid this from happening, galvanized iron 1 is preferred. The flow rate used are 12 US gallons per minute and 10 US gallons per minute. Meanwhile, the friction factor is defined as the ratio between the force required to move a section of pipe and the vertical contact force applied by the pipe on the seabed. Based on Reynolds number for flow in pipe, friction factor can be determined to assess the relative roughness factor. Reynolds number is inversely proportional to friction factor. With flow rate for the first run is 12 US gallons per minute, the friction factor recorded is lower than when the flow rate is 10 US gallons per minute. This shows that the higher the flow rate of fluid flow, the lower the friction factor. Next, we will compare friction factors of different pipe sizes. Friction factor for the 2-inch pipe section is slightly lower than for the 1.5-inch pipe section. This is because the fluid velocity is increased when it flows into a smaller area, resulting in the higher force required to move it. The higher the fluid velocity, the higher the Reynolds number. Thus, the friction factor value also increase. This is the pipe properties table we use to find Fannin's friction factor from the chart. Let's continue with comparison of friction loss coefficient. Friction loss coefficient, denoted as K, is a calculation of the friction loss through the fitting for a particular fluid flowing at a specific velocity, and it is dimensionless. Observing the table, it is proved that K of galvanized iron 1 is higher than K of stainless steel 1. It is for both runs, which are at 15 US gallons per minute and 11 US gallons per minute. This is because the surface of galvanized iron 1 is rougher than surface stainless steel one, making the galvanized iron one have the higher K value. The friction loss through the elbow is considered as minor loss. When the fluid flows through elbows, the effect of friction might be caused by the viscosity of the fluid. The friction loss in the elbows are caused by the flow separation on the inner side of the pipes as it contributes to a greater friction loss. The friction loss coefficient is also considered for the T plus gate valve. It brought changes in each section area where the T is dividing the flow into two other branches and the loss was considerably high. Fluid flow experienced less resistance by flowing through a fully open gate valve as there is no significant resistance in it. While the K value of expander or reducer recorded as the highest among the other two fittings, which are T plus gate valve and 90-degree elbow. This is due to the changes in the area where the fluid is flowing that result in some pressure loss. In a system where the area of the pipe decreases, the kinetic energy is produced due to transformation of some potential energy as the fluid flows through a smaller pipe. Using the Bernoulli equation, the various terms in meter of water gauge is calculated excluding the pump work by choosing 2 points where the pump work is not significant. By choosing the pressure drop between the tapping points LA, the pressure drop and their discrepancy can be seen. The fluid pressure drop through galvanized iron is higher than the stainless steel. It is following the description of equipment where the galvanized iron is said to have a rougher surface. Whenever the internal flow area changes, the fluid velocity changes too. Flowing through a reducer, the velocity of fluid flow is increased and pressure is decreased. While fluid flows through an expander, is resulting in decreasing velocity of fluid flow and the static pressure is increased. As the pipe diameter is constant when running this experiment, the velocity will be constant and no change in pressure. That's why adding kinetic pressure head is not going to correct the discrepancy. There is an error that cannot be avoided when carrying out this experiment. The parallax error happens where some of pressure gauge are set to higher places, causing the reading value becomes less accurate. The precaution steps are taken to action, where before reading the value of pressure drop, it is needed to make sure that there is no bubble in the pipe by pressing the equalizer button. At meantime, it is needed to observe the small tube according to which part correspond to reading values wanted. This is because the reading could be different and further calculation might be slightly far from actual values.
From this experiment, we can conclude that there are several factors that affect the fluid friction in pipes and fittings. The first factor that contributes to fluid friction is pipe roughness, where the stainless steel has a lower fluid friction compared to galvanized iron. This is because the roughness of inner surface of galvanized iron is higher than the stainless steel. Different flow rates also denoted as a parameter where the higher the flow rate, the higher the friction loss. Through fittings part, we can understand that friction loss over expander and reducer is the highest, followed by the elbow, and then gate valve pulse T. Expander and reducer are having higher fluid loss because the change in area will change the velocity of fluid flow, and this causes a higher friction loss among the other fittings.